Tengo dos razones de sentirme contento cada vez que hablo aquí. Una es estar rodeado por almerienses y la segunda es poder presentar a los propios almerienses colegas de distinción y de grandes logros y de mucho poder explicativo. Esta noche me toca presentar brevemente a Carole Mundell, que es la Directora de Ciencia de la Agencia Espacial Europea. Carole nació en Inglaterra, pero de padres escoceses, y fue a la Universidad de Glasgow, y después tuvo una carrera distinguida que pasó por ser catedrática en la Universidad de Bath y tener papeles importantes en la dirección de la ciencia en Gran Bretaña. Y después de eso pasó a la Agencia Espacial Europea. Ella está encargada de muchos programas de gran envergadura y básicamente yo no tengo nada más que decir, que eso habla por sí mismo y está muy bien presentado por Carole.
Muchísimas gracias a todos, John and Pedro. Tonight, it's my great pleasure to join you tonight. I just want to make sure this works. Okay. So it has been my pleasure through my career to work at the forefront of scientific discovery. But my life really changed when I was seconded into UK government to be the Chief Scientific Advisor in the Ministry of Foreign Affairs. And there in particular, I advised the ministers during the global pandemic. After that life change, I came back to the university to do my physics and to teach my students and wondered what next. And it was by great luck that the role at ESA became available. And as Director of Science, I now enable many scientists across the world to do world-leading science with our missions. And I'm really a diplomat, a director, and I bring my scientific knowledge. I don't do research at the moment, but we enable the world's best science to happen in Europe.
Ha tenido la suerte de ser asesora principal científica al gobierno británico, sobre todo durante la pandemia, que era obviamente un trabajo de gran responsabilidad, y después la suerte de ir a su trabajo actual, donde puede influir positivamente en la ciencia en muchos países con muchos científicos, aunque ahora mismo no puede investigar como tal, pero el trabajo que hace potencia la investigación de una forma inconfundible y ella está muy contenta y orgullosa de ello.
So let me give you, first of all, a small introduction to what the European Space Agency is. Hands up, who's heard of NASA? No, me neither. NASA is the American ESA.
Dice, manos arriba que sabe lo que significa NASA. Y dices, bueno, realmente lo que NASA es la ESA americana.
But I'm being serious, ESA is the only international space agency that brings together so many countries. We have 23 member states who all come together to guide us in the kind of engineering, science and technology that Europe should excel in.
Pero la ESA es la única agencia espacial realmente internacional que coaliga a 23 diferentes naciones para hacer espacial puntera, hacer investigación puntera en España conjuntas.
And Spain is one of the founding members of ESA. Last year we celebrated the 50th anniversary of the founding of ESA, and I have the privilege also to lead the European Space Astronomy Centre down in Madrid. Spain is a very strong member state of ESA and has a fantastic scientific community, top universities and also very competitive industry.
El año pasado era el 50 aniversario de la fundación de la ESA y obviamente ESA tiene grandes universidades, grandes científicos y mucha experiencia científica.
And you may be able to see Minister Diana Morant. She's on the far side. She is the Minister for Science, Education, Universities. And the way ESA is funded, once every 3 years, all of the ministers of our 23 member states come together and approve the budget for the next 3 years. In November, we brought our ministers together. It was a very difficult time. There is the war in Ukraine, there's a cost of living crisis in many countries, and we made the case for investment in space so that Europe can have leadership and sovereignty in the world. And the ministers actually funded to the highest level in the history of ESA, 22.3 billion, to be invested back in all of the member state countries for space.
Muestra a Diana Morant, la ministra de Ciencia española, en una reunión de los ministros de Ciencia de 23 naciones miembros, y dice que cada 3 años preparan un presupuesto y en el último presupuesto, a pesar de las circunstancias, la guerra de Ucrania y varias crisis financieras, resolvieron de invertir una cantidad récord en ciencia espacial de 22 billones de euros.
So what does ESA do? Well, I'm tonight obviously going to take you on a whirlwind tour of the space science program that I lead. And 50 years ago, the agency was founded when the European Launcher Organisation was merged with the European Space Research Organisation. But since then, we've diversified into just every area that space affects in modern life. Everything from navigation and telecommunications, through Earth observation, space safety and sustainability, and of course our human spaceflight astronaut program.
La agencia cubre una gama amplia de diferentes aspectos, no solamente estrechamente, cubre observación de la Tierra, cubre obviamente física del espacio y un rango muy importante de diferentes cosas.
So the Space Science Programme, as I say, is the founding backbone of the agency, and my job as the Director of Science is to ensure this first line, to enable European leadership in frontier breakthrough science and technology, and to empower our member states to lead in global space science. And that for me is a very serious responsibility, and I also have to do it within a budget cap, which means I have to develop with our industries across all of our member states new technologies to answer the biggest questions that humanity can ask about the universe.
Y ella tiene una gran responsabilidad de su puesto, que es fomentar la ciencia espacial del más alto nivel del mundo dentro del presupuesto asignado, que implica el desarrollo dentro de la agencia de nuevas tecnologías por mejor eficiencia en todo lo que se hace.
So I'm looking out into the audience and I'm looking for any young people. Do we have any really young people in the audience? Hands up if you have a big question that you'd like to ask about the universe. Shall I give you some hints? Are we alone? Is there life out in the universe?
Are you asking if anyone in the audience?
Yeah, maybe there are some questions.
Sí, pregunta para cualquier persona en la audiencia si quiere hacer una pregunta grande sobre el futuro del espacio o del universo. Cualquier pregunta.
Anybody brave? What's the biggest question you'd like to know about the universe? You're not allowed to ask us. You're an expert. I have a question here.
Si encontraremos un planeta tipo Tierra en otro sistema solar. ¿O planetario?
No.
If we found another planet like Earth.
So thank you for the question, and I'm going to show you in a little while the mission that we will launch in spring next year to search for Earth-like planets around Sun-like stars. So I don't have the answer today, but we know how to ask it and how to fly it. So that's called the Plato mission. Now, anybody got another big question?
Is the European Agency trying to make a permanent base in a moon or another planet? Is there a plan for that?
So that doesn't sit in my work, but my colleague Daniel Neuschwander, who is the Director of Human and Robotic Exploration, is thinking about this right now. At the moment, we collaborate with NASA. So did you see the Artemis mission recently? It was Europe that provided the propulsion to leave the Earth's gravity to go around the moon, and also the human life support system on that. So at the moment, we are discussing with the ministers in Europe what is the ambition that Europe has. Should we do this with international partners, or should Europe do it ourselves? So it's a good question.
It seems right now it's a US-China race. Is Europe having any kind?
So I'm going to stop you because you're asking me politics. I was asking for big questions about the universe. That's a human question. So that's politics for over coffee, right? I'm asking for bigger questions, much bigger questions. Please,
Hello,
madam.
thank you for everything. It's my first time to come here, so
Bienvenidos.
because I come with my voice, so I want to know what is the importance of all these things in the world, in our life.
And I'm going to
Why-
answer that for you too.
Okay, because we are here, but I want to know what is important to know. Because we have to know if there is life in another place, or if we need it, or I want to know what we are here and what I can learn here.
Yeah, and I think that's one of the most fundamental questions. And again, you'll see this in the missions, that we're trying to answer these big questions. So the universe is nearly 14 billion years old, and we are living, thinking creatures for a tiny, tiny fraction of that time.
El universo tiene una edad de 14.000 millones de años y nosotros estamos sacando fotos durante un periodo muy corto.
If we have some feedback.
El universo... No, esto. No. El universo tiene una vida de 14.000 millones de años y nosotros, científicos, hemos sacado fotos del universo durante, bueno, decenas de años, muy poco, muy poco.
Are we alone? Is there life on other planets? Are there planets like Earth around other stars? And what is the origin and nature of the universe itself?
Entonces, una de las cosas que quieren saber es cuál es el origen de las estrellas y cuál es su papel en la naturaleza en general.
Quite good questions. So this is what we try to do. We ask these questions, we work with the scientists from all of our member states to ask very big questions. Then we try to invent and develop the technology with all of our industries, and then we launch and we fly those missions to space. And we either go to somewhere in the solar system, like Mercury or Venus or Jupiter, or to the Sun, or we catch the light from the distant universe and try to decode the secrets that are encoded in that light to help us to understand the physics of the distant cosmos.
Entonces, hay dos formas básicas de operar. Hay dos formas básicas de operar. Una es ir a un planeta cerca, o sea, acercarse y tomar fotos desde cerca o desde su superficie para entender los procesos que ocurren. Y el otro es obtener información de distantes estrellas y galaxias para también descifrar cómo funcionan, cómo se han formado y cómo es su futuro.
And you can see here the missions that we've developed and flown over the last 50 years from Europe. On the bottom, the missions that have flown in the past, and all of these data are available from ESA in Madrid for our scientists. In the middle, the missions that are flying in the sky and doing science now, and at the top, the missions that we're building and we will launch in the future.
Entonces, el diagrama muestra la información disponible en Madrid en archivo para los científicos que lo necesiten. Después, las misiones que están volando ahora mismo, recogiendo nuevos datos, y también las misiones anteriores y sus resultados.
And just to give you a flavour of some of the breakthrough firsts that we've led from Europe, the first ever high-energy gamma-ray image of the sky, the first ever encounter with a comet with Giotto, the most precise measurements of stars with Hipparcos, Hubble, we worked with NASA and contributed world-leading instruments, SOHO the Sun, and Huygens, still the most distant ever landing of a human probe on a distant body. And this landed on Titan, a moon around Saturn, over 20 years ago.
Entonces, la variedad de los proyectos de la ESA incluyen un mapa del cielo en rayos gamma y pero incluyen una muestra de un cometa, coger muestra de un cometa y el aterrizaje más distante de cualquier vehículo, de cualquier otra agencia, que era en Titán, satélite de Saturno.
Never works. And it goes on. Our X-ray mission studying the plasma around the sun, our Herschel mission that looked at the cool infrared light from the distant universe, and of course a very famous one, first time humanity has ever landed on a comet, Rosetta.
Entonces, hay diferentes... el primer satélite para medir con precisión las posiciones de las estrellas, que era Hipparcos, eso antes. Después, el primer objeto para ponerse en un cometa y...
That's fine, landing on a comet, you can't beat that, can you?
Yeah.
Detecting the light from the beginning of the universe and measuring the tiny quantum fluctuations in the dying embers left over from the Big Bang.
Y el proyecto Planck, que es el mapa del fondo cósmico, de radiación del fondo que es del Big Bang, que mostró a nosotros ayer Brian, eso estamos con un satélite de la ESA, Planck.
And I'll take you into the future as we go through the talk, and how we build on what we've learned in the past, both in terms of the scientific questions we've answered and the new technologies that we've developed, and how we use those to do new things in the future.
Entonces nos llevará al futuro explicando cómo han utilizado las tecnologías desarrolladas en el pasado y cómo están desarrollando nuevas tecnologías para el futuro.
And the work that we do is very long term. So I'm looking at the youngest people in the audience and wondering what you might grow up to be. But we will launch a mission that will go to Saturn and will land humanity's first ever astrobiology laboratory on the surface of the moon Enceladus in 2052.
Entonces, tienen proyectos a largo plazo. Está viendo un niño en la audiencia preguntando qué va a hacer cuando crezca. Pero ya tienen un proyecto para volar hacia Saturno y aterrizar en la superficie del satélite Enceladus un laboratorio completo de biología en el año 2052. Así que planifican.
But of course, this isn't new. We're not the first people to look at the sky and wonder about our place in the universe. And 15,000 years ago, ancient Cro-Magnon man, this is a painting actually on the walls of the caves in Lascaux in France. And scientists originally thought these were paintings of wildlife. But then a German archaeoastronomer, Professor Ragengluck, discovered that this is actually an ancient planetarium. And in fact, this is not a picture of a bull, this is the constellation of Taurus, and this is the Pleiades star cluster painted on the cave wall.
Entonces, no somos para nada los primeros astrónomos. Esto es una imagen de la famosa cueva de Lascaux, donde los hombres pintaron pinturas rupestres que se suponía tenían animales salvajes, un toro, por ejemplo, pero resulta que no, que el toro es la constelación de Taurus y que también se puede ver las Pleiades también en el muro en Lascaux.
Now I'm going to speculate because I don't know what these 4 points are here. Maybe everybody can see from the back. But I wonder whether this is the path of a planet moving across the night sky against the fixed background of stars. And maybe these were the first ancient astronomers trying to understand the motions of the planets in the solar system without even yet knowing that other planets existed.
Entonces está admitidamente especulando que unos puntos en ese cueva eran seguimiento de la posición de un planeta a través del cielo, sin saber realmente lo que estaba pasando, pero observándolo, no sabiendo lo que eran los planetas, pero tenían la curiosidad de hacer eso.
And of course this really is something that ancient astronomers did more recently, and I name a few famous scientists here. Copernicus decided to publish a very radical idea that instead of the Earth being at the center of the cosmos, which was the belief at the time, that maybe the sun was the center of the universe. Galileo came along and was an early adopter of modern technology. So the telescope had just been invented, and he pointed it to Jupiter and discovered the moons of Jupiter orbiting around another world. And of course that got him into terrible trouble with the church's teachings.
Pues, entonces, obviamente, históricamente, tenemos aquí a los famosos Copérnico, que postuló que el Sol estaba en el centro de nuestro universo conocido y no la Tierra. Y Galileo, que desarrolló tecnología, mejoró el telescopio, no lo inventó, pero mejoró, y utilizó el telescopio para descubrir las lunas de Júpiter. Y obviamente sus ideas eran heterodoxas en cuanto al catolicismo de su época, como todo el mundo sabe.
And Kepler was an ambitious young man, and I think of Kepler really as the birth of empirical experimental science. And he went to Tycho Brahe's house. Tycho Brahe was a Danish astronomer who built telescopes and meticulously every night recorded the position of planets on the sky. And as myth has it, his house was full of data, and his poor wife, bereaved at the loss of her husband, gave Kepler all the data. Maybe it felt like junk to her. And Kepler spent his life digging through the numbers and trying to find a pattern. He found a pattern, which are Kepler's empirical laws of planetary motion. He didn't understand what caused the pattern, but for the first time he not only could measure where a planet was in the sky, he could predict where it was going to be in the future, and that was revolutionary.
Entonces llegamos a Kepler, que estaba empleado en el observatorio Uraniaborg de Tycho Brahe, el danés, y cuando se murió Tycho, su viuda vio todos los datos recogidos de los movimientos de los planetas como, no, ¿qué es eso? Y me echó todo en las manos de Kepler, que lo utilizó para con gran meticulosidad deducir los movimientos de los planetas, las formas, que dio el poder de predecir dónde se van a poder encontrar.
And it was not until Newton, Isaac Newton, came along and discovered the universal law of mechanics and gravity that we understood why the planets behave as they behave, because it's the attraction, the force of gravity between the sun and the planets that keep them going in an orbit around the sun.
Entonces vino Newton y él estableció la ley de gravedad y cómo funcionó para explicar de cierta forma los movimientos que habían medido Tycho y procurado Kepler organizar a perfección. Y él notó que era la fuerza de la gravedad, pero escuchando a Brian sabemos que no es la fuerza de gravedad, ¿no?
And so the bottom line is observational astronomy, studying the cosmos, helps us to understand the fundamental laws of physics. And taking this more recently, of course, Newton's law of gravitation was very good for some time until Emmy Noether and Albert Einstein worked together to discover the general theory of relativity.
Entonces, ya que la astronomía tiene la bondad de dar pistas vitales a las leyes básicas de la física. Y eso ha ocurrido con Newton y después con Einstein mejorando la ley de Newton.
So this is Einstein's famous equation, and simply put, space-time tells matter and light how to move, and matter and energy tell space-time how to bend.
Entonces, el tiempo y espacio de Einstein se puede expresar que la distribución, la curvatura del espacio-tiempo obliga cómo la materia se mueve, y la materia obliga al tiempo y espacio a hacer curvas.
Now, this is physicists' shorthand, but if we write this out properly, it's actually 10 independent, the challenge Joe, second order, non-linear, partial differential equations. So for the rest of the lecture, I think we'll just do the equations, okay?
Dice que esa es una ecuación básica de la relatividad general y que realmente son 10 ecuaciones no lineales independientes, y por el resto de la charla ella se va a dedicar a las ecuaciones.
At the end, no? No, maybe not. But why do we care about these esoteric equations? It's lovely if you're a mathematician and a physicist and you solve them. There have only ever been 3 analytical solutions discovered. One predicted the expansion of the universe. The second predicted the existence of black holes in nature. And the third predicted ripples in space-time when things like black holes collide. And we've experimentally proven each of those predictions. And then, of course, Brian broke our understanding by finding an accelerating universe, which Einstein didn't predict. So there's more laws of physics we need yet to discover.
Bueno, entonces, la relatividad general en su forma de Einstein predijo la expansión del universo, se podía usar para tal, se podría usar para predecir la existencia de los agujeros negros y sus efectos, y se puede usar para predecir la existencia de las ondas gravitacionales, y estas cosas todas se han observado, pero lo que no se esperaba era lo que descubrió Brian, es decir, la aceleración. Y eso, como siempre en la ciencia, ha abierto a un campo que se suponía parcialmente cerrado, ya no.
And in our everyday lives, Einstein's equations are used on our satellites for satellite navigation. And in fact, if we didn't have the corrections from general relativity and we only used Newton's gravitation, our cars and our sat-navs would not get to the location. We'd be quite a little bit off.
Y como ya cada vez más se conoce que aunque la relatividad general se supone muy arcana y muy del universo a escala grande, sin las leyes de Einstein, nuestros cálculos necesarios para controlar todo lo que tiene que ver con satélites, GPS, todos los términos del móvil, etc., no se podía usar. La relatividad general es muy práctica en el mundo moderno.
And now we have a growing network of satellites above the Earth. And if you care about the satellite infrastructure for everyday life, we also want to begin to protect that environment. And so we come back to the need for scientists to understand the nature of the cosmos to protect our modern space infrastructure.
Y una de las necesidades de entender cómo funciona el universo es para proteger nuestro entorno.
And last week it was my privilege to go to French Guiana to launch a new mission that will completely transform the way we understand the global Sun-Earth system. Our Earth has a liquid iron core and it produces its own magnetic field. And the solar wind, the radiation and energetic particles that come from the sun, bend that magnetic field into a bubble around us, and that's what makes life on Earth possible.
Entonces ella, la semana pasada, estaba en la Guiana francesa para ver el lanzamiento de un satélite, una prueba de la ESA, para explorar la interacción Sol-Tierra en términos de campos magnéticos, que la Tierra tiene su campo magnético, que a su vez protege la atmósfera, protege la Tierra y de cierta forma hace posible la vida.
And we want to understand really when there is a solar storm, when these ejections, so-called coronal mass ejections, when they hit the Earth's magnetic field, we want to be able to predict the aurora and the geomagnetic storms so that we can tell our satellite operators, our ground infrastructures, electrical subsystems to be able to be aware and be ready to protect the systems.
en este caso lo necesario es saber cómo, al detectar una tormenta solar, una eyección de masa cargada iónica del Sol, para poder usar la predicción para proteger todos los sistemas en Tierra que se podían afectar.
So this was a mission that we built in collaboration with our Chinese colleagues. We sailed it across the ocean a few weeks ago. We took it to the satellite launch station and we fueled it and then we launched it last week.
Este es un satélite desarrollado en colaboración con los colegas chinos, y que eso es lo que se lanzó hace una semana.
It was a nighttime launch. It was stunning. It rained all day, and just before the launch, the rain stopped, the clouds cleared, and you can see how it lit the sky. It went from being nighttime in the jungle to daylight, and you can see my team were very happy as we were successful.
No diga que era un milagro, pero estaba lloviendo tremendamente, de repente paró y la condición de lanzamiento hacía posible el lanzamiento, y de repente el lanzamiento iluminó todo el paisaje con luz de día, noche convertida en día, muy impresionada ella misma.
And now for the next month, the satellite itself has an engine and it will start to raise its orbit to 120,000 kilometers above the North Pole. So it's a very elliptical, elongated orbit. It will come down 6,000 kilometers above the South Pole, download its data, and it will make the first ever X-ray images of the Earth's magnetic field, which is making the invisible visible. It will monitor the aurora caused by the coronal mass ejections continuously for 45 hours at a time. We will measure directly the particles coming from the sun and make a measurement directly of the magnetic field, and then put everything together.
Tiene un pequeño cohete que se va a utilizar para elevar la órbita. Será una órbita elíptica muy alargada a 120,000 kilómetros de apogea y 6,000 perigea cerca del Polo Sur, donde puede descargar todos sus datos. Va a hacer imágenes en rayos X de las auroras y detectar las emisiones del Sol también.
So you might ask, how do we know that the sun is doing all of this? Well, first of all, that's what we think the aurora are. But we have incredible missions like our Solar Orbiter mission, which is close to the sun and is actually making measurements of how the sun behaves as we speak.
Pero ESA ya tiene una misión que se llama Orbiter Solar, que está en órbita alrededor del Sol, mucho más cerca, estudiando en conjunto con su compañero Parker de la NASA cómo funcionan las emisiones del Sol.
And indeed, Parker Solar Probe is a little bit closer, but we have better instruments. No, we collaborate, we don't compete. And you can see here you can see here the incredible loops, and these we think are charged particles following the magnetic fields encoded or entrapped into the sun's chromosphere.
Entonces utilizan el hecho de que hay partículas trabadas dentro de lazos de campo magnético del Sol para hacer imágenes y así entender bien cómo funcionan.
But the very special thing about Solar Orbiter is that not only are we studying the sun in unprecedented detail, for the first time ever, we're starting to move a satellite out of the plane of the solar system in which the Earth orbits the sun to above the plane of the solar system to start to take a sneak peek at the poles of the sun.
Y el satélite de la ESA tiene una propiedad única, que puede moverse la órbita para que va no solamente en el plano casi ecuatorial, sino que puede sobrevolar cerca del polo y por primera vez estudiar el Sol desde cerca del polo del Sol.
These are the first images of the poles of the Sun. We're now 17 degrees out of the plane of the Sun. And the reason this matters is because when the Sun goes into its most active phases every 11 years, we think it's because something changes in the magnetic field configuration in the poles. So for the first time we're looking directly at the poles.
Y la razón de hacer eso es que la teoría dice que el ciclo de 11 años de actividad magnética del Sol depende críticamente del fenómeno cerca de los campos magnéticos cerca de los polos. Y eso será la primera vez que eso se puede observar.
And so over this year we will start to use the slingshot effect of the gravitational acceleration as we swing past planets in the solar system to further raise the orbit of the satellite out of the plane of the solar system to reach 33 degrees and get an even better view of the poles.
Y van a usar el efecto de gravedad que al atravesar cerca de un planeta puedes usar la energía gravitatoria que impacta el planeta para cambiar más radicalmente la órbita y así sube para obtener mejor vista de los polos.
And we have many important milestones coming up this year. So our Bepi-Colombo mission, which is on its way to Mercury. Mercury is the planet closest to the Sun. And maybe you can see here, I wanted to give you a sense of the environment in which Mercury lives. This little black spot here is Mercury on a loop, eclipsing the limb of the Sun. So it's hot, it's hostile, lots of radiation, lots of charged particles, and our Bepi-Colombo mission is on its way to orbit around Mercury.
Y la misión Bepi-Colombo de la ESA está ahora mismo rumbo al planeta Mercurio, que obviamente al estar tan cerca del Sol está en un ambiente muy hostil, muy caliente, y van a explorar este ambiente.
So it's a very hostile environment, like flying into a pizza oven, and it's the first time ever we visited Mercury, not just with a spacecraft, but with two daughter spacecraft. And when we reach the orbit of Mercury, which has been technically very difficult to do, we will launch these two probes, and then we will study the whole planet and the environment.
Y esta vez, no es la primera vez que una prueba llega cerca de Mercurio, pero esta es más sofisticada. Tiene dos hijuelas que van a sacar para hacer geometría y diferentes medidas a la vez.
And it's taken us a long time to get there. We launched in 2018. And the one thing to know about the solar system, because the Sun makes a dent in space-time, in the inner solar system, if you travel towards the Sun, your spacecraft speed up, and so you have to slow down. So what we've been doing is trying to slow down to get captured into the orbit of Mercury. When you go in the other direction, the Sun is pulling you, so you have to speed up. And we don't have rockets powerful enough to make us speed up, so we use these gravity assists around other planets to accelerate us to the outer regions of the solar system.
Este uso de planetas para acelerar estas pruebas es muy importante. En el caso de Mercurio, lanzaron esta prueba en 2018 y obviamente si mandas la prueba directamente hacia el Sol, la gravedad del Sol domina de tal forma que sería imposible pararlo para entrar en órbita alrededor de Mercurio. Lo que tienen que hacer es poco a poco ir en espiral hasta llegar con la velocidad apropiada y pueden hacer la órbita. Y en la otra dirección, los Voyager, los que han ido hacia afuera, el Sol intenta pararlos y no hay cohetes suficientes para lograr las órbitas que llegan hacia el borde del sistema solar. Usan los planetas para pasar al lado e impartir energía y momento y echar el cohete hacia el borde del sistema solar.
But as we've been on our journey to Mercury, we've made many passes of the planet and made measurements. So we did one pass where you can see the antenna from the spacecraft. We were just 165 kilometers above the surface of the planet. We also made the first ever thermal image of the surface, and there are elements and materials on the surface of the planet that we don't yet know what they are.
La prueba de Mercurio ya han pasado al lado del planeta y han llegado a pasar 365 kilómetros de la superficie, han podido hacer imágenes de la superficie, imágenes térmicas de la superficie, para además intentar saber su composición, y hay resultados que tienen que todavía no se entienden.
On another pass, we managed to map the entire magnetic field structure of Mercury with just 30 minutes as we whizzed past the planet.
Y en una de las pases al lado del planeta consiguieron medir todo el campo magnético del planeta en 30 minutos de tiempo al pasar al lado. Sí.
So let me ask a question. Are there any students in the audience? Hands up if you're a student.
Estudiantes, por favor. Identifíquense.
Okay, so I'm going to give you a little bit of advice. If you go to a scientific lecture and you fall asleep, fine, you study hard, that's understandable. And you wake at the end of the seminar and you want to look clever to your professors, and of course you're clever. You scratch your head, you raise your hand and you say, but what about the magnetic fields?
Yeah. Okay, entonces está dando un poco de ideas cómo comportarse. Eres estudiante, trabajas duro, te cansas, vas a la conferencia y al cansarte te duermes, y de repente al final te levantas y ahora despiertas y quieres parecer inteligente, eres inteligente, ¿no? Les dices, tengo una pregunta, ¿qué pasa con los campos magnéticos?
It always works. 9 times out of 10, the speaker will say, oh, that's a really hard question. They're fundamental, and I don't know. But please don't ask me that question, because then I'll know you've been asleep.
Sí, la respuesta es sí, qué buena pregunta. Los campos magnéticos son fundamentales, muy difíciles. Yo no sé la persona que lo sé, tengo que preguntar a otra persona.
So, in a few months' time, in September, watch the news, because we then have a very tense time. We start to do the transfer into the Mercurian orbit, and we start to release our daughter crafts, and then we start to do science at Christmas.
En septiembre habrá noticias porque la prueba la sonda va a entrar en órbita Mercurio, van a echar las hijitas y van a empezar a hacer medidas. Entonces, eso se espera, que va a salir en las noticias.
Another planet which we won't reach until the 2030s is Venus, and Venus is very similar to Earth, but very different. It has a runaway greenhouse effect, it has very hot temperatures on the surface, and we will develop a mission called Envision that will fly to Venus and do similar types of aerobraking orbit to get into the atmosphere of Venus, and to measure everything from the surface of the atmosphere down to the geological core of the planet, and answer the question, why is our sister planet so different to Earth, and could that be our future?
En los años 30 van a lanzar una sonda a Venus. Venus es de cierta forma la hermana de nuestro planeta, pero aunque es similar en unos sentidos, es muy diferente en otros. Por ejemplo, tiene un efecto invernadero descontrolado, y de hecho Venus es el planeta, la atmósfera más caliente, la superficie más caliente del sistema solar, más que Mercurio, tal y como es su atmósfera. Y van a enviar una sonda que puede medir desde la superficie de la parte alta de la atmósfera hasta la superficie y hasta el corazón del planeta sólido para dar respuestas y intentar responder a la pregunta si nuestro destino será también como Venus.
We know a little bit about Venus, but of course we won't get a direct view of the surface as we will for Mercury, because there's a very thick oxygen-rich atmosphere. So we have to develop very special materials to make sure our spacecraft doesn't dissolve in the Venusian atmosphere.
Pero no pueden hacer lo que hace en Mercurio, que es tomar imágenes muy directas. Porque si entran en la atmósfera está muy densa, muy caliente, tiene mucho oxígeno y esta sonda desintegraría.
And of course we still want to know whether life could have existed on Venus.
Bueno, y todavía quieren saber si hubiera posible algo de vida una vez en Venus.
Now, on the other extreme, we'd like to know whether the cold, icy moons around Jupiter are actually habitable for life. We know that there are liquid, salty oceans underneath the icy crusts, and our JUICE mission, which launched in 2023, is on its long journey out to Jupiter to tell us the answer as to whether those moons could be habitable for life.
Otra misión de la ESA se llama JUICE y se lanzó en 2023 y va a acercarse a varios satélites de Júpiter para ver que sabemos ya que tienen océanos salados dentro de sí o en la superficie y para ver si hay alguna posibilidad de vida en estos satélites.
So we won't land, unlike the mission to Enceladus, but we do have 10 very powerful instruments to study everything that we can about Jupiter and its icy moons.
No van a aterrizar, pero tienen muchos instrumentos para estudiar Júpiter y sus lunas heladas.
And it will also help us to understand Jupiter-type planets in other solar systems, because we're finding many Jupiters outside of the solar system. So this will give us a handle on understanding the search for habitable worlds beyond our own solar system.
Y dado que ya sabemos que hay muchos planetas del tamaño de Júpiter en otros sistemas solares, cuanto más sabemos de nuestro Júpiter, más podemos entender y evaluar las posibilidades de vida en otros planetas.
We'll also study the planetary plasmas, and I'm sorry to keep saying this to the students, but the magnetic fields.
Hay otros que van a estudiar plasmas y, con perdón, campos magnéticos.
It was a beautiful launch on the Ariane 5 rocket. This was my first ever rocket launch that I went to, and before the rocket was launched, I stood in this tunnel. The gases coming through here were at 1200 degrees Celsius, and obviously I wasn't standing there during the launch.
What was this one? I didn't hear which
This
one.
was the launch of JUICE.
El lanzamiento de JUICE fue el primer lanzamiento donde ella asistió en persona. Ella estaba muy cerca y obviamente impresionada por los gases a 1200 grados, pero claro, no puede quedarse.
JUICE was on its way. It was a beautiful launch, and this is a series of photographs that JUICE took of itself looking back at the Earth.
Y son fotos hechas por JUICE de él mismo mirando la Tierra.
And JUICE has a very complicated journey. I've already told you about this gravity assist, this slingshot effect where you can speed up as you swing past a planet or a moon. And in fact, this is the speciality of JUICE. So we've already done the first Earth-Moon flyby. We've also done a gravity assist around Venus. We have another one coming back past the Earth, and you can see we do this many times till we wind it up to the speed to be able to fly off directly towards Jupiter.
Esta sonda usa sus pasajes alrededor de la Tierra-Luna, la Tierra y la Luna y Venus, varias veces, cada vez adquiriendo energía para finalmente lanzarla hacia la zona de Júpiter. Y eso ya han hecho varios pasajes de ese tipo.
Sounded very cathedral. This is the flyby between the Earth and the Moon. So we did a free lunar mission. We took measurements of the Moon, and on this side here you can see we switched all of the instruments on and we looked back at Earth because we want to ask the question, could the moons of Jupiter be habitable? So the first test is to look at the planet that we know is habitable and see if we can find that out. And I'm very happy to tell you, Earth is habitable.
Entonces, una cosa que hicieron durante esta maniobra gravitatoria era sacar fotos de la propia Tierra y claro, si quieres saber si un planeta u otro es habitable, sacas la foto de la Tierra para ver sus aspectos y después puedes compararlos con otros planetas. Ella dice que bueno, al final han descubierto que sí, que la Tierra es habitable.
Which is good news, and long may it last. So, as I said, we're now developing our mission to follow on from JUICE, learn everything that we've developed in our technology to go out to Enceladus. And Enceladus is an icy moon of Saturn. There is a liquid ocean underneath, but there are cracks in the ice, and plumes come from beneath the ocean. So we'll fly through the plumes and look for microbes, and then we'll land on the surface and make some measurements to look for life.
Enceladus, que es un satélite de Saturno, donde van a también enviar una misión, es un planeta helado, literalmente con hielo, con placas muy grandes de hielo, pero con agua debajo y con grietas en el hielo donde se escapa vapor de agua. Estos han hecho fotos en el pasado, diferentes sondas, y eso los van a explicar, van a explorar con la misión a Enceladus.
We're still designing the mission. We have some concepts, and we will very soon in the next year or two figure out exactly what the design is. And we have a very tight timescale because we have to launch in 2043 when all the planets are aligned in the right way, because we have to arrive to land on the south pole of Enceladus when it's illuminated by the sun in 2052.
Entonces, esto ya están en el diseño del proyecto y tienen que lanzar en 2042 para lograr el alineamiento exacto de los planetas que puede procurar la llegada de la sonda al Encelado cuando el polo sur está iluminado por el Sol durante 2052.
It's a long time to wait, so in the meantime we will follow up from Rosetta and we will launch Comet Interceptor, which will be a little mission with 2 daughter craft on it that will fly out to deep space, wait for a pristine comet to come from the edge of the solar system or an interstellar object, chase the comet, launch the 2 daughter craft and study.
Entonces, dado que tienen cierta impaciencia, no quieren esperar tanto para hacer las cosas, van a preparar un proyecto sobre cometas donde lanzarán una prueba, una sonda hacia una parte más profunda del espacio y después esperarán allí hasta que aparezca un cometa desde lejos o desde la nube de cometas del propio sistema estelar o incluso uno de los interestelares, y después le van a cazar y observarlo. Ese es otro proyecto que tienen en mente.
And the reason we want to do this is because we now think that the solar system is 2 times bigger than than we ever thought it was before, and there's a lot of material out there that we're learning about the origin of the solar system.
Eso es en parte porque sospechan que el sistema solar tiene el doble del tamaño antes pensado, y hay muchas cosas que se pueden aprender de las partes en el borde.
And as I said before, not only are we learning so much more about our own solar system, but we're very quickly learning about other solar systems. And so next year we will launch the Plato mission, 26 identical cameras, to study stars that have planets orbiting around them, and we will look for Earth-like planets and habitable zones around Sun-like stars, so Earth 2.0.
Entonces van a lanzar un proyecto que se llama Plato, que el año que viene va a observar las estrellas donde ya sabemos que tienen planetas, pero la observación es con precisión para poder detectar planetas tipo Tierra. Es relativamente difícil detectar planetas de tamaño de la Tierra, porque un planeta tamaño de Júpiter, por ejemplo, es mucho más grande y tiene más efecto tanto en la luz como en la gravedad de la estrella. Encontrar una Tierra necesita mucha más precisión. Eso es lo que van a hacer en completo.
And in the images behind you just saw images of the spacecraft with the cameras, and it's now been through all of its testing, where we shake our beautiful satellites, we heat them, we freeze them, we do terrible things to them, and if they survive that, we know they're good to go into space.
Entonces, eso muestran las pruebas que los pobres satélites tienen que sufrir, vibraciones intensas, frío, calor, líquido, y si sobreviven, entonces han aprobado y pueden ir al espacio.
We're very confident. We think there are going to be many solar systems out there because we know that there are billions of stars in our galaxy, our Milky Way galaxy, and we know there are billions of galaxies in the universe. And in fact, the Gaia mission, which we retired last year after 11.5 years of operation, has given us a revolutionary view of over 1 billion stars in our own Milky Way galaxy.
Entonces, sabemos ya que debe haber muchos planetas en la galaxia. Sabemos las posiciones de 1.000 millones de estrellas o más desde el satélite Gaia, que ha mapeado en 3 dimensiones nuestra galaxia de una forma revolucionaria. Voy a hacer un comentario. Los proyectos y barcos y Gaia son realmente muy sencillos, simplemente miden posiciones y velocidad también, uno por uno, de estrellas individuales. Es muy aburrido, una, otra. Y claro, la NASA no parece muy glamoroso, pero entre ellos han revolucionado el campo de la astronomía. Entonces en esto, ESA ha sido un líder indiscutible.
And fundamental. And this just says in one plot what you said so eloquently, John, that it took 2,000 years, all the way from Hipparchus through Landgrave to Tycho Brahe, Flamsteed. You can see her date here, 150 BC, medieval times, Victorian times, to get 1,000 times improvement in measuring the position of stars and how they move. It took 2,000 years to do 1,000 times better. When Gaia came along and we went to space, we did 10,000 times better in 25 years.
Sí, durante 2.000 años el ser humano había mejorado su habilidad de precisión de medir estrellas por un factor 1000. Y con Gaia en 25 años esto se ha mejorado en 10.000 en 25 años. Eso da una idea muy gráfica de lo que se ha hecho. Es una maravilla. Yo que he utilizado los productos de Gaia, hablo del corazón.
And it's revolutionized astrophysics, and as you said, John, that one image, which is a dot-to-dot picture, it's not a photograph, has actually revolutionized all areas of astrophysics. We've found about 150,000 asteroids in the solar system, 350 of which have moons orbiting around them, all from measuring how things move and how things wobble very, very precisely.
Y no solamente lo de las estrellas, sino dentro del sistema solar han detectado 350 nuevos asteroides, algunos que tienen compañeros. Realmente ha sido, y en la ciencia eso es en general, cuando añades 1 o 2 plazos decimales, aunque no parece nada, normalmente es mucho.
It's transformed our understanding of our own home galaxy, the Milky Way. We live about 2/3 away from the centre of the galaxy. It's very hard to study your own home environment, but Gaia has given that vision to us and also told us that our galaxy has a warp and it wobbles about.
Sí, es más difícil de medir nuestra propia galaxia que otras, porque vivimos dentro de ella, es como vivir en un bosque y es más difícil encontrar lo que pasa, pero si miras arriba al cielo lo ves, es realmente el mismo efecto. Y Gaia ha descubierto también el alabeo de la, bueno, no lo descubrió, lo midió, yeah, he didn't discover the ball.
Confirmed
Measured
it,
it.
mapped it more accurately. I agree, thank you. What it did discover were new black holes. So we know at the centre of the Milky Way there is a supermassive black hole, about 3 million times the mass of our own sun. What we did not know was that there are stellar mass black holes 10 times the mass of our sun, a minimum of 3, wandering through our galaxy.
Y descubrieron algo muy nuevo, un rango de masas de agujeros negros, donde no sabíamos que existían, que eran como en el orden de 10 a 50 veces la masa del Sol, donde había un hueco en la población y Gaia encontró 2 o 3 de ellos.
The scientists are now analysing all of the Gaia data. We will have a new data release 4 later this year, and then the whole lot will be analysed uniformly, and a 5th data release, and we expect to find many more of these stellar mass black holes.
Y están reanalizando los datos de Gaia con más precisión aún y esperan al final de este año encontrar más de este tipo de agujeros negros.
We don't know how to form black holes that are 20 or 30 times the mass of the Sun. There are no stellar models that tell us how to do that. But the reason I care about them is because they're going to be the cosmic calibrators for our LISA gravitational wave interferometer.
Todavía no se sabe cómo en la práctica cómo se forman agujeros negros de este tipo de masas, pero son importantes porque dan lugar, su fusionamiento, su fusión, dan lugar a ondas gravitacionales, entonces se permite medir sus distancias sobre grandes distancias de una forma totalmente independiente de los supernovas tipo 1A, por ejemplo, y entonces un proyecto LISA de la ESA va a aumentar nuestro conocimiento de la estructura del universo utilizando este efecto.
And LISA will be the first ever space-based gravitational wave interferometer. So we will fly 3 identical spacecraft together. We will launch them into space. On board, each has a very pure gold test mass. And that test mass must fall through space without knowing that it's on a spacecraft.
Entonces, LISA tiene 3 satélites separados por grandes distancias y dentro del centro cada uno tiene una esfera de oro que debe caer libremente en el espacio sin saber que está dentro del satélite.
And LISA will orbit on the same orbit as the Earth orbits around the Sun, and the distance between each of the spacecraft will be 2.5 million kilometers, and they will be aligned with lasers to within a precision of about the size of a proton.
Los tres satélites de LISA están a distancias de separación, un triángulo de tamaño 2,5 millones de kilómetros, conectados por láseres y con una precisión del tamaño de un protón a esa distancia.
And if supermassive black holes collide in the distant universe, or something catastrophic happens at the beginning of the universe to disturb space-time, those ripples come through the cosmos, a bit like if you throw a stone into a pond. And those ripples, by the time they reach LISA, will make the spacecraft wobble a little bit, and the distance between them will change by a tiny fraction. So we will literally measure ripples in the fabric of space-time.
Entonces, eso es lo que va a pasar, que si dos agujeros negros se fusionan o se fusionaban hacia el principio del universo, los efectos de las ondas gravitacionales van a llegar a LISA y van a producir un movimiento detectable, y eso nos va a poder, entre otras cosas, medir la distancia de la ocurrencia de esta fusión, independientemente de la luz.
It's incredible technology, and I'm a little bit scared to be the director of those programs.
Es una tecnología tan impresionante, pero dice que tiene un poco de miedo de ser la directora del programa que incluye la LISA.
Well, they're very good engineers. The other part that I just want to finish with is the hot universe and then the dark universe, and especially for John. So the hot universe, we think that, we think about 5% of the universe is made of ordinary matter, atoms, stars, humans. And half of that is at a temperature higher than 1 million degrees, and we don't know why.
Well, sabemos bastante bien que 5% de la masa del universo son átomos normales, como nos explicó ayer Brian. Solo 5%. Pero este 5%, alrededor de la mitad, son átomos a temperaturas de millones de grados en el espacio, básicamente, que son muy difíciles de encontrar. Esa es la invisible materia baryónica, que se dice.
So 2 years after we launched LISA in 2035, we will launch the world's largest X-ray telescope ever to have been built. We're building a test facility that's 3 stories high just to test the optics, and that will give us the most unprecedented view of the hot invisible universe in X-ray light that humanity's ever seen.
Y entonces, ESA está construyendo un satélite que se lanzará en el año 35 aproximadamente para mapear en rayos X el universo, que sería sensible a la emisión de este gas, que en otras longitudes de onda es transparente, no lo vemos. Y eso es otro proyecto que está preparando ESA.
And last but not least, I want to introduce my favourite mission. I'm not allowed to have a favourite. I'm often asked, what's your favourite mission? And it's like asking, which is your favourite child? But Euclid is a very, very special mission, and we call it our dark detective.
Y ahora va a terminar por lo que es su misión favorita. Y admite que no se puede tener una misión favorita, es como no poder tener un niño favorito, no se puede. Pero bueno, ella ya lo va a explicar.
Okay. So, as you heard from Brian yesterday, 95% of the universe is unknown. So we think about 27% of that is dark matter, and the rest is a thing called dark energy, or something that we invoke to understand the accelerated expansion of the universe.
Entonces, como dijo ayer Brian, 5% del universo son átomos normales, 27% es la materia oscura y el resto, en el orden de 70, es esta que se llama energía oscura, para tener un nombre.
So, if we're going to answer Brian's question, we need a very special mission, and Euclid is that mission. So what we have here is very, very sensitive detectors in optical and infrared bands. We also measure the spectra of galaxies, and we have a very wide field of view that can do in a single snapshot the area of 2.5 times the size of the moon. 2.5 times the size of the moon in a single shot.
Okay. Entonces, este satélite que ya está en órbita tiene muy sensibles detectores en el infrarrojo invisible y un campo en el cielo muy muy grande, 2 veces y medio el diámetro de la Luna, su longitud, su dimensión.
And astronomers always ask for either spatial resolution, so the ability to see detail, sensitivity and field of view. And you can usually only have 2 out of 3. With Euclid, you get all 3.
Astrónomos que hacen imágenes piden 3 cosas: sensibilidad, posibilidad de resolver pequeños objetos y un campo muy grande. En casi todas las observaciones, los instrumentos, puedes obtener 2 de los 3, pero Euclid tiene todos los 3.
And in the next 6 years, we will survey the entire extragalactic sky, so everything outside of the Milky Way that Gaia studied, back to a time 10 billion years in history. And we will do that fully autonomously because we can't do this one patch at a time, but the telescope will do it completely automatically.
Y van a mapear todas las galaxias que pueden hasta una distancia que corresponde a 10.000 millones de años sobre todo el cielo, pero se tiene que hacer de forma automática, no pueden interrumpir el programa y apuntar a algo, no es eficiente, tienen que observar automáticamente preprogramado.
And I want to give you a sense of the first images. So when we launched the satellite to commission the instruments to check everything was working well, we spent 24 hours taking some very special images. And you can start to see the detail as I play through.
Al principio, para simplemente comprobar las buenas imágenes de los instrumentos, pasaron 24 horas solamente tomando imágenes en detalle.
You can see beautiful grand design spiral galaxies like our own Milky Way galaxy.
Entonces, aquí veis galaxias espirales tipo Vía Láctea.
You can see star clusters.
Cúmulos estelares con muchas estrellas en algunos casos.
And then we can zoom in to little stellar nurseries, glowing bubbles.
Entonces, zonas de nacimientos interestelares, nacimientos de estrellas, donde las nuevas estrellas están inflando el gas alrededor y ionizándolo.
We checked our instruments by looking at famous parts of the sky, like the Horsehead Nebula. Everything was perfect.
Entonces también la resolución mirando objetos famosos como la cabeza del caballo, que está súper conocido y funciona perfectamente.
And not only were the images beautiful, but they told us that we could do the science that the mission intends to do. And what the mission needs to do is map out the dark matter. That's the matter that we don't detect light from, but we can see how it distorts either the light from galaxies behind or the space-time around it, and also measure the expansion of the universe and the weak lensing, strong and weak lensing, so that we can figure out how the dark matter couples to the dark energy.
Entonces, obviamente, la idea es intentar mapear la materia oscura, pero o no lo ven. Lo que ven es los efectos en la forma de las propias galaxias, en otra en la forma de torcer la luz que tiene la masa de galaxias, es decir, las muy lejos, los agujeros muy lejos mandan la luz alrededor de galaxias más cercanas, y esas sirven como lentes, y la forma de la imagen final te dice la distribución de masa que incluye la masa oscura.
And you can see an example here. This is a massive galaxy cluster. There are many thousands of galaxies. There's hidden dark matter that acts like a lens, and these arcs are actually stretched out images of galaxies far, far behind this galaxy cluster, whose light has been distorted through this dark matter lens.
Entonces, esa es una imagen de un cúmulo de galaxias, pero algunas de las galaxias son curvas, y estas curvas son imágenes de galaxias muchísimo más lejos que están distorsionadas por el campo gravitatorio del cúmulo, el propio cúmulo, y eso dice que podemos medir la distribución de la materia oscura.
It's making the invisible visible. We also know at the centres of galaxies. So this is now one galaxy nearby, and there's some starlight, and we think that there's a gravitational lens, so a distortion due to the dark matter at the heart of this galaxy. But from the ground, the picture is quite fuzzy, and it takes many, many years with telescopes on the ground to try to study such a system.
Es el centro de la galaxia donde se sospecha que hay materia oscura, pero para obtener una imagen con nitidez suficiente desde de la Tierra sería mucho tiempo, muy grandes telescopios, pero con una imagen en Euclid tienes la nitidez.
But looking with the sharp eyes of Euclid, right at the centre of this galaxy, we found a perfect Einstein ring, or a gravitational distortion.
Utilizando Euclid, con esta, encontraron lo que se llama un anillo de Einstein, que es una de las formas que tiene la luz de la galaxia detrás a enfocarse delante y rendirse visible. Hay varios tipos de anillos de Einstein que normalmente no son muy completamente anulares, sino tienen arcos y puntos más brillantes, pero al final es un anillo.
And I'm told about 4 of these types of systems were known, but with Euclid we then found about 500.
Antes de Euclid conocían media docena de estos anillos de Einstein. Con Euclid ya conocemos 500. Se da una idea de su potencia.
We have a lot of work to do. So we will ultimately map 9 billion galaxies back in time to 10 billion years of cosmic history.
Al final de la misión de Euclid van a mapear 9.000 millones de galaxias hasta una distancia y tiempo de 10.000 millones de años luz.
And just to give you a sense of the magnitude of the data, this is one shot with Euclid, so the size of the full moon, 2.5 times the size. And this was the first mosaic that we managed to stitch together with just a few weeks of data.
Entonces, eso para dar unas muestras, hay una imagen de Euclid con su tamaño, y eso es un tipo de mosaico de varias imágenes de Euclid que han puesto juntos para tener un campo muy grande.
So we found 100 million cosmic objects in just 1% of the final survey.
Encontraron 100 millones de objetos cósmicos en solamente 1% del cartografiado.
And so to finish, I want to thank you for your attention and interest. I want to thank John for his outstanding interpretation and added scientific knowledge. And when John has translated my thanks, I'll ask for the house lights to go down and I'll let you enjoy the music and the tour of a tiny fraction of our Euclid cosmos.
Entonces, ya muchas gracias, me ha dado las gracias. Siempre agradezco. Y que ella va a decir ahora, al bajar las luces de la sala, podemos tener con música una pequeña vista de los productos de Euclid.
Bueno, vamos a empezar el turno de preguntas. Por la hora que es, no podemos hacer muchas, pero aún así se podría. Que levante la mano el que quiera decir algo y por ahí el micro, por favor.
Hello? Okay. First of all, thank you for your work and for this beautiful last image. And my question is about magnetic fields. No, it's a joke. It's a joke. No, my question is about which is the relationship between ESA and artificial intelligence. Is a tool that you are actually working on, or it's not useful for all of you? Thank you.
Sure. Thank you. Shall I answer magnetic fields or artificial intelligence? No. We are using artificial intelligence. In fact, it's something that has been pioneered in the field of astrophysics for many years. We've always called it machine learning. We used it for Gaia, we're using it for Euclid. It's not possible to study 9 billion galaxies and even more cosmic sources one by one. So the discovery of the 500 gravitational lenses at the centers of the galaxies in one data release, use machine learning techniques. So we train the models, we use citizen science, so you can all join a galaxy zoo type thing and help us to classify. So we use citizens practicing to train our models, and then we confront the data. So it's a normal practice within our field, I would say, fundamental.
Se ha dicho, inteligencia artificial durante muchos años en astronomía se llama aprendizaje por máquina. Obviamente en un proyecto como este sería absolutamente impensable analizar datos de millones y millones de objetos sin utilizar métodos de aprendizaje por máquina. El descubrimiento de los 500 agujeros negros espaciales, etcétera, etcétera, todo se ha hecho utilizando lo que se puede llamar inteligencia artificial, pero no es inteligencia, hay que entrenar el proceso y utilizan ciudadanos, es decir, para la ciencia de ciudadanos, como se llama, Galaxy Zoo, la Zoo Galáctica, y sus seminarios para entrenar el programa, y el programa después hace el trabajo.
Buenas noches. ¿Qué relación tiene la energía oscura con los agujeros negros y por qué la mayoría de galaxias tienen agujero negro en su centro?
What's the relationship between dark energy and black holes? That's one. And why do most galaxies have a black hole, big black in their center?
Very good questions. So we don't know which comes first, the galaxy or the black hole, and we think that the first generations of stars may produce seed black holes. So we know that there is a strong relationship between the mass of the central black hole and the mass of the galaxy, and we want to understand how that happens. So is it that when material falls towards the black hole and it's ejected, there's a feedback loop that helps to grow the galaxy? Or is it the other way around? Did the galaxy seed, did the black hole grow the galaxies? We also think galaxies merge and the black holes merge. Lisa will test that. And your question on black holes versus dark energy, we don't know, but we think that they're not related directly because black holes are gravitating objects, so they may sit in the dark matter part. The dark energy, I think, is physics. Brian probably talked about this yesterday, new physics that we have to understand. What Euclid is trying to do is map the dark energy, wherever it is. Lisa will tell us about the black holes. And then the combination will also then tell us how the dark matter and the dark energy behaves as a function of time in going back in history. Because that's the big question. We don't know whether dark energy evolves with time, and then we have to adapt our physics.
Bueno, la respuesta sobre las galaxias y los agujeros negros, ella dijo que al principio de la formación de las galaxias en el universo probablemente se formaron agujeros negros y no se sabe directamente si ellos se formaron y atrajeron más materia para formar la galaxia o si la galaxia se estaba formando y su campo gravitacional centro formó el agujero negro. Yo puedo añadir una cosa: existen galaxias sin agujeros negros masivos en sus centros, que es una respuesta parcial a esta pregunta. En cuanto a si la energía oscura tiene que ver con agujeros negros, probablemente no, porque los agujeros negros son masa, son gravitacional, y la energía oscura es algo diferente.
Hablabas de Encelado, que tenía unas grietas en el hielo por donde salía un vapor. Ese vapor, ¿qué puede ser? ¿Que el agua interior esté caliente, sea condensación? ¿Qué puede ser?
Okay. So you talk about vapor escaping from the cracks in Enceladus. What is the vapor? Is it water? And if so, why is it escaping? Is it hot?
Yeah, so we don't know what the vapor is. We think it may be a pressure effect. It's very cold at Saturn. So when we landed on Titan, we expected to land in oceans of methane, but actually we landed on frozen riverbeds and the boulders were frozen methane. Now, we think on Enceladus it's not methane. We think there's ordinary water, and there might be a pressure effect that are causing these water geysers. So they're not hot, but there's a pressure effect. We hope that by flying through, there's some hints that there may be prebiotic molecules in those plumes, and if we find the same on the surface, we then connect, if you like, the symptoms of life in the ocean and on the surface.
Bueno, probablemente es agua, son agua, el vapor y gotitas de agua, las plumas del Encelado. Probablemente no es cuestión de gran calentamiento, sino de presión que está expulsando la materia. Pero de todas formas, el proyecto sería para ver si hay posiblemente moléculas prebióticos asociadas con estas plumas y posiblemente indicios de posible vida. Eso es lo que van a hacer con la misión.
Wonderful talk, Carol.
Thank you.
I was tempted to ask you about polarization in gamma reverse, but I won't do it.
You have to ask about the magnetic fields, and then I can tell you about polarization and gamma ray bursts. You know the answer.
Of course. No, but I wanted you to tell us about the FAST program in the European Space Agency, in particular Arrakis mission, which is led by Spain, because I think it's important that you tell us about what's the idea behind.
Sure. So the Arrakis mission builds on the technology that we developed for Euclid, and it is a small, fast mission using existing technology. So it's a binocular telescope. It is being brought into the program if our member states agree in 2 weeks' time. 2 weeks' time we will go to Tenerife for our science program committee, which are the 23 member states, who will decide whether the mission is ready for implementation. So I hope that they will give me permission to build the mission. We've done all of the prototyping, we've improved the sensitivity of the detectors, and the scientific question that Arrakis will answer is, how do galaxies get built up? So we will be looking for what's called missing dwarf galaxies. There's a problem in cosmology that there are not enough small galaxies. And because it will be able to see the relics of galaxies forming and interacting, it will basically do galactic archaeology.
Hablando de Arrakis, Arrakis es un proyecto modesto basado en tecnología extante y todavía no está aprobado, pero en 2 semanas la reunión de la comisión de los 23 miembros de la ESA va a ocurrir en Tenerife para decidir, y ella expresa su deseo que se lo van a aprobar. Y una parte de su misión es buscar las galaxias enanas. No son suficientes para acordarse con los modelos actuales de la formación global de las galaxias. Entonces, la idea de Arrakis es buscar con más ahínco estas galaxias enanas alrededor de galaxias más grandes.
Thank you. And I should say, sorry, that it's a very strong Spanish lead with our colleagues from Sweden and Norway and Switzerland in particular.
Entonces es un proyecto liderado por España con colaboración con Suecia, Noruega,
Switzerland, Sweden and Norway.
Y Sweden.
Thank you very much for your excellent presentation and all the work you people are doing. Now I understand that you have studied how to protect the health and to increase our long-term survival. According to your data, does the sun temperature increase over the time? Or I'm asking because I want to know the possibility or no of ejection. And could the Earth, in its gravitational motion, can move closer to the sun, or according to the data, is only to know. Thank you.
Okay. So the temperature, the average temperature of the sun is very stable because it's what's called a main sequence G-type star. So it's burning hydrogen at its core and it makes it very stable. What I showed in the images here are the effects of magnetic reconnection. So this is almost what we call solar weather. So the core temperature of the sun is very stable and will be for many millions of years. Ultimately, the hydrogen will finish and there'll be helium, and then the sun will contract and the temperature will change and helium will start to burn. And that's a normal stellar cycle until finally, long after we're gone, the core will probably be carbon, nitrogen, oxygen. I'm testing my stellar physics here now. And each time the burning stops, the star can't hold itself up, so gravity causes it to shrink. The pressure increases in the center, the temperature rises, and it starts to burn new elements. And that's how we get all of the elements in us. We're made from stuff that's burned and cooked in stars.
Okay. Bueno, la temperatura en el centro del Sol es muy estable. El Sol es una estrella que se llama la secuencia principal, que está cambiando y fue el hidrógeno en el centro. Y en el Sol hay fuel para 5.000 millones de años todavía, antes de que tiene que cambiar y empezar a quemar helio y después carbono, nitrógeno, etcétera, etcétera. Y esto es muy estable, con lo cual la temperatura del Sol no va a subir sistemáticamente. Y todas las catástrofes que al final van a ocurrir, van a ocurrir hace tanto tiempo que no es muy preocupante.
La última.
Hi, Carole. Thanks for your lecture. It's been really interesting.
Thank you.
And it's a privilege for me being here listening to someone like you. I don't know if this is a very scientific question, but anyway, I'm going to ask you. If for you, in the past years and decades, science has been related to spirituality, etc. And I would like to know if for you, if some relationship between astrology and spirituality, like God, the universe in general. That's one question, and related to another, that is, which is the most stunning experience that you have had in your life as an astronomer? I suppose that there must be more than one, but if you could tell us. Thank you.
That's a very profound question. I think as a scientist, I am always stunned by how powerful the scientific method is. Hypothesis, test, confirm or reject. And that scientific method has been handed down to us for hundreds, maybe even thousands of years, as I hope my talk presented to you. So there is something very human about studying the cosmos, asking questions about our universe, however big or small that universe feels to us. And there is something that connects us all today across many nations, but also back through history. And that, for me, I think, is very spiritual in the sense that, as I said, the universe is nearly 14 billion years old, and we are sentient, thinking beings. We can conceptualize the universe, we can form a hypothesis, we can discover the mathematics that describes the universe, we can form the hypothesis that creates a test, that we can then invent the engineering, fly it to space to make a test on that hypothesis and confirm or deny it. I think there's nothing more profound than that.
La cuestión es algo profundo, algo espiritual, la pregunta. Y la respuesta es que María, el método científico, tal y como lo hemos recibido desde el pasado, con sus ideas de proponer ideas y poder dar pruebas prácticas, y después las pruebas prácticas sirven o para aceptar la idea o para rechazarla o modificarla. Y eso es un proceso muy, muy potente y nos ha dejado llegar a un punto donde somos pequeños seres sentientes en un planeta, en un sitio, pero podemos concebir todo lo que hemos podido concebir sobre el universo y después diseñar métodos para ir y comprobarlo. Y eso, para Carole, es de por sí espiritual, en el sentido es el espíritu humano avanzando, que a pesar de ser ínfimos, somos capaces de concebir el infinito. Y eso para ella y para muchos científicos es muy espiritual.
Thank you. And the second part of your question, I think you asked me the most exciting thing. So that, yeah. There are two things I would answer there. Many, many exciting things, but on a very small level, as a research scientist, when you make a discovery and you, at that moment, are the only person in the world or in the history of humanity who knows that thing. The feeling after that is, it's probably wrong, and I should check or try to break it. And the other most exciting thing is going to a rocket launch and seeing not the rocket go up, but the teams who have worked for many years to make that a reality.
Bueno, la segunda parte de cuál es la cosa más emocionante, y ella tiene dos respuestas. Una es cuando, como científico, has descubierto algo nuevo y en este momento eres la única persona en el mundo y posiblemente en el universo que lo sabe. Y después de un momento de pensamiento piensas, bueno, a lo mejor no es así, a lo mejor me equivoco y hay que comprobarlo. Es una cosa. Y la cosa más emocionante de otra forma era ver el lanzamiento de un cohete con un satélite de este tipo, pero no es un cohete, son los equipos que han contribuido a esto, que están ahí expectantes y viendo su aparato lanzado al espacio.
Bueno, tenemos que acabar porque se nos ha hecho un poquito tarde hoy. Quiero agradecerte, Carole, que hayas venido a Almería a nuestras jornadas, sabiendo además que estás siempre muy ocupada. Te lo agradecemos infinitamente y te vamos a dar un aplauso por haber venido.